a bit more, we can wait maybe 3 minutes.
No, but you tell, I don't know how did you organize it. So the organization is by your side. So I'm totally trusting you, and so you tell me when. I know that you're gonna tell me once that I should start, so I will start at that.
Yes, no problem. Thank you. Yeah, I think. Yeah, it's just okay. Just 2-3 minutes. We can wait at least if as many as people
but
are.
you tell me, and you know it's 8 o'clock in the morning by my side.
Okay.
So I have all my time the whole day. So
okay.
No worry.
Okay,
no
thank
worry
you.
about that.
No, hopefully, yeah, as we planned, yeah, we can start just, we can, it lasts for just 1
you
hour.
Tell me,
Yes.
it's not urgent, and so you tell me if we need to wait a little, it's not bothering.
Yes, just a bit, yeah, just 2-3, just that's what, and we can just start. Yeah, 1 minute, maybe more, and because I'm wondering some people
so I'm
here
going just to look for my phone, and I will be back. Okay. So
okay, sure,
1
sure.
minute.
Okay, sure,
See
sure.
you.
Yeah, take your time. Yes, see.
Hello.
Hello, Haiba. Hi.
Yeah.
How are you?
Okay. So no problem when Hossein can't, like we can start. Yeah.
Yes. Yeah, and unfortunately, I don't know what's problem with my Teams, and I am logging through via web, not the app application. Yes.
Why?
I don't know what happened. It just today it happened to yes, but it's okay anyway. I am now connecting via web. Yes.
Okay. Okay. So I think we can start now.
Yes, I think we can. Okay. So everyone can see my screen. Haiba, is it clear?
Yeah. Yeah. I can see.
Okay, great. Thank you. Thank you so much. Hello, everyone, and thank you to this webinar series, payment webinar series. I am Ali Rahman, hosting this initiative, in fact, with the aim to enrich the academic environment at our university, Southwest Jiaotang University, by inviting distinguished and international scholars, researchers, and experts in the different domains of payment engineering to share their insights and expertise and as a speaker in this webinar series. And in fact, the core objective of this initiative is to expose our students and to the forefront of research, and also our, including the faculty alike, to the forefront of the research and the latest advancement in payment material and structure through this payment webinar series.
Hello,
yes.
Eli? I think you can change your PPT, yeah?
I can change, what do you mean?
Like, I think the screen is different.
Yes. Okay, so let me, okay, so let me, maybe there is something wrong, yes.
Yeah.
Yes,
I think you can share yours.
Okay, is it okay now?
No.
Okay, so let me, I check. Okay, share. Okay, maybe I will stop and then I start to share again.
Okay, no problem.
Okay, let me. Okay, yes, that is right. Okay.
Oh, still the same.
It's still the same. Okay, sorry. Let me see. Still.
But you know, on the top you have the. I think that you are just sharing your window. You need to share. I mean, the different boxes, and you need to choose your computer.
Yeah.
Right. Yeah. This is what I am doing, and
normally it should work.
Yeah. Is it work? Is it?
No, it's fine.
Whether my
it's fine.
That's fine.
Yeah.
Okay.
Yeah.
Okay, that is great. Okay, thank you so much again. Okay, so yeah, continuing to my introduction today, I am very pleased to introduce our speaker, Dr. Hossein Nowamooz from National Institute of Applied Sciences in of Strasbourg, France. Dr. Nowamooz is very good, my friend, and actually he has joined the Department of Civil Engineering at the INSA of Strasbourg, first as an assistant professor in 2009, and then as an associate professor from 2015. He completed his BS bachelor's degree in civil engineering at Sharif University of Technology, followed by a master's degree in geotechnical engineering from the University of Tehran, both in Iran. And then following to that, Dr. Nowamooz got his PhD in geotechnical engineering from the University of Lorraine, France in 2017. Then where his research focused on the swelling and shrinkage behaviors of expansive clays. His research focus, Dr. Nowamooz, lies in the hydrothermomechanical behavior of geomaterials. And during his academic career, Dr. Nowamooz has authored and co-authored over 37 journal articles on granular materials, expansive clays, shallow geothermal systems, and ram earth materials. Dr. Nowamooz also played a pivotal role in establishing and contributing to numerous projects at the European, national, and industrial levels. And in the meantime, his editorial responsibilities include serving as an associate editor for the Journal of Current Trends in Civil and Structural Engineering, and which further, and also the reviewer of several international peer-reviewed journals, which further underscore his dedication to his research and further improvement and dedicated to advancing the field of civil engineering. In today's presentation, the title of Dr. Nowamooz's speech is hydromechanical behavior of the granular materials. Before I give the floor to Dr. Nowamooz, I would like to mention that after Dr. Nowamooz, after his presentation of his speech, we will have a Q&A session, and I hope all audience will actively participate, especially our students, to whether they have any question, they can type their question in the chat box, or they can raise their hands directly, turn on their mic, and ask their question from Dr. Nowamooz. So here in the also chat box, when you can type your question here very easily. Okay, thank you again, everyone. Thank you, Dr. Nowamooz, for accepting my invitation. It's a privilege to have you today in our webinar. And now it's your turn. Thank you.
Can you hear me? Just first of all,
yes,
I need to check. And can you see my screen or not yet?
Yes.
Okay.
We can see your screen very clear.
Okay, perfect. First of all, and before starting my presentation, I should thank you, Ali, for first of all invitation, and secondly for all the description that you have done. Actually, I have prepared some slides also on this issue, but we can go faster on these slides. So thanks again to be with you today, and so to give me this chance to present my work. Before going through the title, so maybe it's not bad that I represent myself in a way that in France we have somehow a typical way of let's say associate professor, because I am associate professor in Department of Civil Engineering in INSA of Strasbourg, Institute of National Applied Science. in Strasbourg, but at the same time, we are participating in laboratory, and so our laboratory, it is named differently from our school, and so we are a member of, I am a member of eCube laboratory.
Pardon, Hossein, I don't know, sorry for disrupting you, whether you share your screen?
Yeah.
No, we cannot see your screen actually.
Okay, so I'm going to do it again. So
sorry for interrupting this. Thank you.
So that's why I was asking that I was thinking that you. So do you see it now? The presentation? Can you see it now or not?
Hello, I think you can you open your PPT?
I have opened it. Actually, at the beginning, I asked it was working. So
strange, it is still, yeah.
So I'm going to do it again. Normally, you should see it right now. Am I right or not?
Yeah, we can see now.
Yeah, okay,
see
so perfect. I'm going to. It's fine. Just I need the confirmation. It's fine for everyone.
It's fine.
Okay, perfect.
Yes,
so let's go.
Thank you so much.
So the title of presentation, as was mentioned, is going to be around the granular material. I am basically in geotechnical engineering, and I have done some things around pavement structure. So mainly you will see today my presentation will stay around the soil and the geotechnical part. If it is necessary if you would like to contact me, I have put also my email address, and so for any questions about the presentation and the other points, feel free to contact me, and it's going to be a pleasure to answer you back. I think that this slide, I can pass it a little bit fast because Ali has done this presentation. So you can have a general look there about my PhD, especially, it's about the soil shrinkage of the expansive soils. Then, I was in Strasbourg since 2009, and there's something like, I don't know whether habilitation that we need to do. So I did another, let's say, diploma. It's higher than PhD, and so I was able to become associate professor, and I have my research group since 2015 in Strasbourg, and so all the things that you may see, it is coming also from the different projects that we have on this field since 2009, and then after when I became completely the supervisor of the work. I am not only working on the granular material.
Hossein, sorry, excuse me again for disrupting. It seems your PPT, your presentation is not moving. It is just stuck on the first slide, and very strange. Yes, now it's moving, and it is not full screen actually. Even it's not full screen, and
when I go through full screen, is it changing? Now is it changing?
No, it is not full screen, and
it is good now.
It is moving, but it's not full screen.
But I'm doing it full screen.
Very strange that.
Okay, no problem. I think some setting problem.
I can change it here. I can change
no problem.
the size.
Yeah, that would be good. Yes.
Okay, thank you.
So if it's moving like this, so I'm going to stay like this. So I was telling that, is it fine now? I need the confirmation.
Yes, it's fine. I think it's okay. We can see.
So just to say that I'm not just working on the granular materials, and so I am also working on clay materials, some works about the geothermal storage system and heat storing methods that they are also related to geotechnical engineering. And recently I've done some works about the local soil, the ram dirt materials that they can be used also in the construction. If I want to give a general idea or general title about all of the things that I'm doing, I am doing the thermo-hydromechanical or chemo-thermo-hydromechanical coupling in geomaterials. And so all the things that they are touching this coupling, these couplings, it is somehow related to my work. And the pavement is also one of, let's say, the one of the field that I can work on it, because we have the atmosphere, because we have the soil, and so we can have the interaction, the hydromechanical or thermohydromechanical interaction inside the soil. If I need the confirmation, do you see the next slide?
Yes, we can see, Hossein. Yeah, it's now
perfect.
on the next. Yes.
Okay, so generally, if we come back again to my field of research, it's going to be around geomaterials, and as I told you, it is going to be the thermo-hydromechanical coupling work. It should be mentioned that when we have the soil, because of these interactions that we may have with the environment, with the structure, we can imagine that this soil is going to change its state several times. It is moving from its saturated state to its unsaturated state. And so the reason that I'm doing all of these couplings is because the soil is not going to remain at one state in its whole life. And so these changes, it is going to be coupled. If it's on the pavement, you can imagine that they are the vehicle that they are going to pass through the pavement structure. It's going to be some rainy time, and so it's going to be the precipitation, or we have the thermal variation all over the life of the soil. So now, if I'm imagining that this soil is going to be a part of pavement, so I need to consider the hydromechanical behavior of the granular material. If it's a part of individual building that I have put the foundation inside a clay soil, it's going to be the hydromechanical behavior of clay soil. And if I'm going to use the same soil for the energy storage methods, and for example for geothermal usage, so it's going to be the hydrothermal behavior. So it depends on the field, it depends on the demand, it depends on the subject that we are treating. It is possible that we don't need to consider the totally thermo-hydromechanical coupled problem. So we need to choose one part. And so mainly for what I'm going to present you today, I'm going to stay by the hydromechanical behavior of the granular material. So we are going to stay majorly on the pavement. I think that this slide that I'm showing you, even it is written in French, it is going to talk with you, because in the pavement structure, you have the first layer that it is going to be the asphalt layer. Then I'm going to be down, and so I have my base layer. And if you want, you have the sub-base or sub-grade layer. And so what is going to happen, and generally, this is the main idea of my presentation, that you see the problems generally on the asphalt layer on the surface, and you say that, okay, all the time that you are passing with your car through pavement, you say that there is some rotting, or there is some surface cracking, and so mainly you say that, okay, this is maybe because of the surface. But truly, maybe it is not only because of the asphalt layer, but it can come also from the base or sub-base layer. Especially, I'm talking about this water level that you can see, because of the rain that it is arriving, no matter by, if you imagine that your asphalt layer is permeable or impermeable, or by the other side, finally you can change the water level. And if I'm going to put it up or down this water level, you can imagine that you are changing the water content or the water state of your granular material. This is exactly what I want to talk about it. You have almost the same loading on the top, the same, let's say, number of cars that they are passing through your asphalt layer or your asphalt pavement structure. But what is happening is that you don't have the same soil with the same hydraulic condition on the top, on the bottom, and so these changes under the same mechanical loading, it can it can provide, let's say, some accumulated deformation that by time you see something like the disaster that they are shown in these two pictures. I'm saying that all the problems that you have in the asphalt layer, they are not only coming from asphalt layer, and they can be attached to the hydromechanical problem of your granular material also. And so in this presentation, I'm going to show some works that we have done on this field, and it can help you to see at the end what I mean by all of these changes and how can we consider it in the laboratory and then in the real scale these changes of hydraulic behavior of the soil that they are attached to the mechanical part. So let's start the presentation. And so for the first slide, maybe you know it, maybe you don't know it, but I need to start my presentation with this fact that the water content of the soil is changing all the time. And so this is related to something that we call it in the field of unsaturated soil suction, the negative pore pressure. So it means that if your soil is saturated, you are somewhere here, can you see my presentation or not? Just I need your...
Yes, Hossein, yeah, we can see, although it is not the full slide, but we can see, yes, we can see.
Okay, so
full screen, yes.
Now it's fine. So I'm saying that this water retention curve, the variation of water content with the suction, you can see that we are on the saturated state, and if we put the soil through its dried condition, you can imagine that you are moving first maybe on the drying path. And another issue that I want to talk about it is that you may have something like hysteresis phenomenon, that there is a difference between your drying path and your wetting path. It means that if I'm in winter and I'm going through the summer, I'm going to be on the drying path. But if I'm on the summer and I'm going through the winter, so I'm going to be on the wetting path. So all the seasons that they are passing, the soil also, they are not going to follow the same wetting and drying path. One point that we need to consider, and this is, the major difference between the reality and what we do in the experimental, in the laboratory, is that we do the things fully. But what I mean fully, it means that you start fully from the saturated state and you finish by totally dried condition, and vice versa. You start from totally dried condition and you finish by totally saturated state. This is the main, let's say, hypothesis that I'm going to do, the extreme condition that I may have, that in the reality, maybe you are not on the totally dried or totally saturated. So you are going to be something between these two, and you are going to turning around, between the wetting and drying paths in the middle of this path. So we are putting ourselves, when we do the things in the laboratory scale, in the extreme conditions. So we may say that if it happens in the reality, in the extreme conditions, we may have such a problem then later. So this is the water retention curve that I wanted to start my talk with it, the variation of water content with the different initial state of the soil. So we should not forget that, as I told you, we are in the winter and then we go to the summer. What is changing in the meteorological condition? It is the temperature, it is the relative humidity, it is the wind speed. So there are lots of hydrogeological information that I may need to create my wetting and drying path. I am able to do it, let's say with the boundary conditions, with the real meteorological condition, I am able to find out what is the drying and what is going to be my wetting path. Now, another point that I need to talk also about the water retention curve is that we are able in the literature to fit, once we have the variation of the water content with the suction, experimentally, we can also fit the curve and we have the knowledge. I don't know whether you know all of these models, but the most important, the most popular model on the water retention curve that we use and I use majorly for our either analytical solution or numerical simulations that we do. So it is the Van Gunuchten equation that it is related to the saturated and residual state, and there are two parameters mainly that we need, alpha and m is related to n at the same time. So if we feed the parameters of alpha and n, we are able to fit our experimental curve, and so we may have the variation on the wetting and on the drying. This is good. We have the knowledge, and so actually, if you do the unsaturated soils, you may have already known these curves and these variations. But what I'm going to change in my work is that I'm going to take this water retention curve that we know it very well in the literature, and I'm going to do something like my approach, my personal approach to this curve. And so there is a reason behind this. You will see a little bit later why I need to change, to modify the things in this approach, especially for the granular material. So I know my curve on the wetting and on the drying path, especially I can fit it, as I told you, with Van Gunuchten equation, or no matter the equation that you may need. But I changed this nonlinear variation to something like, I will call it the linear approach. So instead of having the nonlinear curve, you will see that I'm going to replace my SWRC by three lines, three linear parts. The first is for the saturated states. Then I have a very, let's say, rude slope here, that it is going to be the major part of my SWRC, and then I will reach the residual state, and it's going to be the final state. So I'm going to divide my nonlinear curve to three lines for each step. So the intersection of each part, I may need to define it. I will use something like S star to say the intersection of the first and the second, and I'm going to use SR, another letter, to define the intersection of the second part with the third part. And as you know, I am on the wetting and I am on the drying path. So there is a hysteresis. There is a difference between these two curves. And so I need to define it for the wetting and for the drying parts, these, let's say, intersections with each part. So I repeat, I'm going to replace my nonlinear curve with three linear curves, and the intersection of each part, it is going to be defined by S star or SR. So why I'm doing this? A little bit patient, and so you will see the results, and the answer is on this slide. Because if I'm going to replace my nonlinear curve of SWRC by three lines, and I'm going to change my representation curve to normalized water content based on normalized suction that it is divided by S star, you can see that both curves of wetting and drying paths, they are existing, the hysteresis exists, but if I change the representation in another plane, and I'm going to use normalized water content with the normalized suction, these two different paths, these two different curves, they are becoming unique in this plane, the normalized water content, the normalized suction. And so instead of needing to fit my curve several times, at least twice time, for the wetting and drying paths, I may need just one unique curve on both wetting and drying paths. And so it is going to be represented by this plane. I know that you are good in math. You need to write your equation. It is a linear approach in logarithmic scale. And so your equation, especially this is constant, but I'm talking about this slope. You may need a linear slope that I'm going to come out from here. And so you can relate your normalized water content to your normalized suction with a slope that it is called gamma. And so you write your equation, and so it seems that with one parameter gamma, I am able to reproduce my water retention curve. And especially what is amazing about this approach is that you have one unique curve for the wetting and for the drying paths. Is it fine for now? Is there any question or not? Is it fine? I don't see my Teams. Can you hear me?
Yes, we can hear you, Hossein. Yes, we can hear you clearly and your slide. Yes.
Okay, so is there any question? I may go to the next step. And so if I have my theoretical approach, now we go to the laboratory and we do some measurements. And the objective of this part is to show you that maybe my approach is going to predict well the things. And so it's going to be something that it can explain as well as I can the hydromechanical behavior of my granular material. So I'm in the laboratory scale and I need to fabricate the samples to measure my SWRC. As you said, as I told you, I need to have some experimental results. Then I'm going to fit them with the Van Gunochten and I'm going to replace their Van Gunochten equation by my linear approach. So I use these two methods and you will see that the results that are going to be presented a little bit later. This is for the SWRC, and we should not forget that another major point of this presentation is the hydromechanical behavior. So then after, I'm going to fabricate the different samples at the laboratory scale for the triaxial test. I don't know whether you know this test or not, but we are able to do the repeated loading triaxial test. We can cycle axially and radially our samples in the triaxial condition. If you need to know about the triaxial condition, you put a confining pressure inside the cell and then you add something like axial pressure after, and so this is going to be your deviatoric stress, and then you have your normal stress, and you can cycle let's say by time to have your variation of stress by time. I can do the cycle for the confining and for the axial force, and so for the deviatoric stress. And the objective is to obtain this curve, the variation of the strain or deformation or displacement by time, that it is going to be the number of cycles that I do. Two behavior, they are majorly known because of the loading of the car that we have on the pavement. It is supposed to be cyclic loading, and so this deformation is going to be plastic, the permanent deformation. You are going to have the stabilization after several number of cycles. And there is another part of behavior that we can imagine that after several years, after several cycles, the granular material, it's going to show something like a reversible behavior, and you are going to load and unload your soil, and so it's going to become to the same point, the behavior becomes elastic or reversible. So to do such, I will call for the permanent deformation. I need to do something like conditioning phase. And then there is the next step that I do it at different stress paths, and I will have my reversible behavior. To do the conditioning phase or something related to the permanent deformation, I'm going to do it because of the frequency that I'm using, and so to stay in phase, I need to do it on the stress path QP equal to 3. The information that you have, it is for one stress path at the frequency, and I will do something like 10,000 cycles to reach this stabilized condition. After reaching the permanent deformation and this stabilization, I will do on the different stress paths another frequency. I can do 100 cycles. I am in phase in these at this lower frequency, and so I am able to do it for the other stress paths. The things that it was not possible for this case, let's say, at the higher frequency. And so I can even study my reversible behavior at the different stress paths. And so this is what you can see after that for the experimental results. So I'm going to divide my presentation also in two parts. First, I will show you the results about the permanent deformation, and then we go through the reversible behavior. The objective stays same. We are going to show you the hydromechanical behavior. It means that there is a hydraulic change of the granular material. I'm going to combine it with the mechanical behavior. Let's go through the results. The material that I'm using is a material in France that we know it. Majorly, it is used for the subgrade soil. It is coming from Isiaq region, and it is the sand that we know it very well in our laboratory. The maximum grain size is less than 31.5 millimeter. The fine content that I'm going to show you, it is changing because each time that the material was sent to us, we do again the let's say the geotechnical investigation on it, and so it was happened that in 2 times of reception of material we had 2 different fine contents. This was not what we were expecting, but it opened something like that we are going to have 2 different materials, and all the results that I'm going to show you, which is coming from 2 different times that the material was sent to us, and so we had 2 different materials with 2 different fine contents. First, I'm going to call the material with 4% of fine M4, and the second, I will show you another material. The exact fine content was 15.3, and so this is the second material that I'm going to show you. So you will see in parallel 2 different materials with 2 different fine contents, and the hydromechanical variation that I'm going to show you. Another point to show the same point, that the pore size distribution of the 2 soils of 2 granular material, the 15.3 or 15% of fine, and the second is going to be M4 with 4% of fine. Another curve that I can show you is the compaction curve, the variation of the dry density with the water content with the optimum point. This optimum point, it is important because it's going to be something like our referential initial state that I'm going to use it in the other slide. So something like around 2 megagram per meter cube or 2000 kilogram per meter cube, that it is going to be our optimum dry density. And another point that maybe I'm going to come back again to this point is about the optimum water content. It's around, let's say, between 9 and 10, somewhere here. You will see that the material behavior also is going to be dependent to this optimum water content later. So I need to fabricate, to prepare my samples in the laboratory scale. When I do the triaxial test, I need something like 150 or 15 centimeter of diameter and something like 30 centimeter of height. It's a big sample that I'm going to use for my hydromechanical behavior. The material should be compacted in 7 layers. It should be mixed well with the water content as I'm changing the water content. So I need to prepare several samples, and all of the things that you are going to see is let's say that it was not easy to prepare each time the samples, and so it was very time consuming. And all of the things that I'm telling you, it's about the wetting pad, and if I want to do it on the drying pad, it is even more time consuming, because I need to prepare all the samples first at the water content that it is somehow, let's say, around my saturated states, and it is 12.3 in this work, with the dry density, as I told you, around 2 gram per centimeter cube or 2 megagram per meter cube. And then I need to wait something like around 1 week to 3 weeks to come back to dry back, because I'm on the drying pad, and so to dry back my samples, we use an oven of 35 degrees to come back again to a water content that it is changing between 7 and 11. So for the wetting, let's say, it was easier and faster, and for the drying, we needed even to wait between 1 and 3 weeks to have our final samples. Now the experimental results, and I start with my SWRC. My SWRC, the experimental points, you can see them. They were fitted left side of my presentation with Van Gunuchten curve, and right hand of the slide, you can see the linear approach that I have presented it at the beginning of my presentation. So mainly you can check the gamma parameter, as I told you, as the main parameter, and you have the parameters of Van Gunuchten. Another point that I need to confirm that, yes, for sure, when you use your Van Gunuchten equation, you have more accuracy, but I can tell you that even with my linear approach also, we are not that much bad. And so this is going to be a replacement of a curve with another one. Yes, for sure, maybe we are somehow less accurate, but at the same time, we are going to be good at the other simulation, and you will see it a little bit later in the other slides. This was the results for M4. I can do the same thing for the other soil with the fine content of 15.3, and so you can see the same, the experimental results, the approach with the Van Gunuchten curve, and then the replacement with the linear approach, and you have also the gamma parameter, that it was the main parameter that I may use for my simulation. Another point also that we are almost in the same range of accuracy for the Van Gunuchten and linear approach. So to tell you that even with the linear approach for some curves, we may have some better approximation also. Then the other stage is the mechanical behavior, that it is going to be coupled with the hydraulic state. So as I told you, I'm going to divide my presentation in two parts. First, I'm going to talk about the permanent, the stabilization after 10,000 of cycles that we have, this part, if you want. And I know the curve of variation. I may need something like this epsilon p max to have it for the different water content. The rest of my curve, the variation with the number of cycles, I need a parameter of f that I fixed it for all of my curves. So this part of equation will not, let's say, modified hugely in my simulations, but I may need this epsilon p max, that it is dependent to water content. And the curve that you can see it at the bottom of my slide, that it is showing you this epsilon p max variation, this range that you have it here, this finalized stabilized state that you have it here after several cycles, that it is going to be related to the water content. You can see that we are on the wetting path for this curve. So I will show you the results on the drying path a little bit later, but for now we are on the wetting path. And so you can see, let's say, let's analyze these results, because there are some good idea that I can show you on these results. First, the permanent deformation, they are somehow low for a water content that I think that I talked about it. I remind you that it is something like around your optimum water content. So if I have a water content less than optimum water content, it was between 9 and 10 if you want, and so we are in this range. I have a water content less than 10, and so in this range, let's say that the permanent deformation, they are very low. And another point that it is interesting is that the permanent deformation of my soil with fine content of 4%, it is higher than my material with fine content of 15.3%. So I have an effect of fine content also on my results, that it can be expressed like this. Then I will reach my optimum point, and the water content, that it is higher than water content of optimum. And you can see that this behavior is going to be modified. It means that the fine content is going to absorb water. And so the permanent deformation of my soil with higher fine content, it is going to be higher than my material with 4% of fine content. Then I have fitted this curve mathematically, if you want. I wanted to relate my permanent deformation to water content for both soils. And so you have something like exponential variation that we have proposed. I needed to define the parameter of another parameter B to relate my permanent deformation to water content. You have the equation here. This epsilon P max is dependent to the water content. It is changing. So I'm starting with the water content at the saturated state. The saturated state in this work is supposed to be 12.3. So I have my water content at this stage, and I have fitted this curve with a parameter of B that it is related also to water content of your sample. We are on the wetting path. We should not forget about it. And then there are some slides that I'm going to show you what's going to happen on the drying path. Now stay again on the wetting path. This is the variation of permanent deformation. The stabilized state, this was the epsilon P max that I have shown you before. Now we have the variation of curve with the number of cycles. Let's say the part of this part of the curve that I have shown you here, this part that I told you that it is constant, I need to define the parameter f for all of the samples, and I can have this variation by the number of cycles. If you want, it was considered f constant for all of the samples. So these are some experimental results that you have, the variation of permanent deformation with the water content and the number of cycles. And I'm going to show the same results also for 15.3. I am on the wetting path now for now. The difference of behavior, as I told you, for the lower water content, the permanent deformation of M4 is higher than M15.3. All of the things that I have told you, you can also see it in this slide. Now I have my behavior, my mechanical behavior, my permanent deformation behavior on the wetting path. As I told you, I want to do hydromechanical coupling, and another point was the behavior on the drying path. Now I want to find out what's happening on the drying path. And for this, I will remind you again the linear approach that I proposed at the beginning of my presentation. So it was the normalized water content on the plane of normalized suction, that it becomes unique for both wetting and drying paths. And so we had a unique curve with a unique slope of gamma that I have defined it before experimentally. And so what I'm going to use is that, okay, my curve is unique in this normalized plane. If I change my plane to another normalized plane, that it is now the normalized permanent deformation, that it is changing with normalized suction, I'm going to say that it is going to be the same also on this plane. It means that I'm going to have a unique curve for wetting and drying paths if I'm going to define everything in my normalized plane. This time it's going to be the normalized permanent deformation based on normalized suction. Already I have shown you all of the things happening on the wetting paths. So I have this curve that it is varying with the normalized permanent deformation with normalized suction on the wetting path. And the objective is, by writing some, let's say, simple equations, to have everything that it is happening on the wetting path to define it on the drying path. And if I write my equation, I can see that if I know my B that I have shown you before on the wetting path, I am able to define my B on the drying path. And so I can find on any paths, if I have the behavior on these paths, I'm able to define it on the other paths. And this is going to be what I'm going to show you later. There are some results that we have found on the drying paths. There are some results that we have it on the drying path. On this plane of MP 15.3, you can see that in the normalized plane, I have the unique wetting drying paths, and I have my results on the wetting paths or on the drying paths that I can define. We need to calibrate some parameters, especially parameter B, that it is going to change between the drying and wetting paths. And so all of the things done to have the unique curve on this normalized curve. And so normally I should show you what's going to happen on drying and wetting paths. I start with the wetting paths, the comparison between my experimental results and my prediction. You can see that I have a water content of 7.5 for experimental results, that it becomes 7 for my approach, my linear approach. and maybe 11, 10.8, there is a difference. But I have the error, but let's say that the predictions, they are good. And especially what is important is the next slide, that I am able also to predict my results on the drying pads. I have some differences, this almost the same differences that I have on the wetting, that I'm going to have it on the drying pads, but the results on the drying pads also, they are acceptable with this linear approach, and so I'm able to repredict the things on the drying pads. And so you can see that I need to calibrate some equations, and each time, I'm able to have the results on the other pads. And so all the time that we have the analytical solution, let's say, I have my linear approach, I have my model of variation. There is another approach that I like to do it. When I do the laboratory scale test, I use some analytical solution to define the behavior. And I think for the last stage, it is not bad that if you have some easily provided equations, to inject them in a code, and so to do some numerical simulation. And for this part, just to show you, maybe it's somehow hypothetical, this part that I'm showing you, but let's say that if we are in the real scale case, and so if we have a pavement that it is constructed with these two soils that I have shown you, M4 for the base layer, and for subgrade soil we have M15.3. The asphalt layer, let's say, for me, it was considered to be elastic linear behavior with the thickness that you can see. So the main difference is going to be the water content of granular material and subgrade material, that they are changing by time. If we are in the humid state in winter, I suppose that the water content of M4 is close to the saturated, and M15.3, because it's down, it is close to optimum point. We have an intermediate state that it is shown with water content of 10 or 9% for M4 and M15.3. And in dry conditions, summer, let's say, we have a 7% of water content and 8% of water content for M15.3. The variation of water content for M15.3 is less than M4. M4 is closer to environment, to the top surface, and M15.3 is down and it's on the bottom, so we have less variation of water content. And so if I'm looking for the deflection of my pavement, I can see that there is an effect of drying and wetting. There is a difference. And especially in the humid season, I will have the maximum deflection, either on the wetting or wetting pad. So it's around, let's say, 1-2 centimeter of deflection, which is becoming around 0 in the summer, because the soil becomes more rigid, and so I have less deflection. The objective was to show you, let's say this numerical modeling is somehow hypothetical, because I am in the extreme condition, as I told you at the beginning. But at the same time, we can say that if 1 year I'm going to activate the extreme weather condition, I may have something like this huge deformation, and I'm going to be ready, let's say, by time, if I'm going to have the extreme weather condition. Ali, how much time do I have? Because I have finished for the permanent deformation. For the reversible behavior, it is almost the same. I will show you the same variation. I can summarize it. Tell me, how should I manage the things?
Yeah, I think Hossein. Okay, so I think Hossein, yes, you can. If it is the same, just if you can briefly move on and finally summarize.
So I will try to finish in 5 minutes. Is it fine?
Yeah, that would be great. That is fine. That's fine.
Okay. So for this was the first part, the permanent deformation. Now let's talk about the reverse. I'm not going to detail the same. You will see almost the same results, the same mechanical and the hydraulic effect that I want to show you. I am on the wetting and drying pad. The main idea is going to be the same, to show you that I have hysteresis. I have the difference between wetting and drying pads, and so I will obtain the same, let's say, difference at the end for also the reversible deformation. The only difference is that I have more results because of the frequency that it is lower. I can do it on the different stress pads that I was not able to do it for the permanent part. Now I have more experimental results, but the first slide that I'm going to show you, that let's see wetting, drying, different stress paths. I have a different, and I have this extreme variation that you can see it for the different soil. It is for M4. I can do it the same for M15.3 if you want. I have a difference of, you see there is a variation of deformation on the wetting and on the drying paths. Another good point is that for the reversible behavior, I can have the volumetric strain and the deviatoric strain. So I have even more information to show you for the reversible behavior. So I can have the variation of deformation with water content at the different stress paths. And so this is the coupled hydromechanical behavior that I wanted to show you, and so I'm able to define them. For this part, I'm going to use another theoretical approach. I'm not going to use my linear approach that I have proposed you, because I have already for the reversible behavior a very good model, Boyce model, that it is developed, and so I'm able to define the volumetric and the deviatoric strain with the stress paths that I have used. I use the concept of effective stress if you want. There are some parameters to be fitted, and so I am able, just briefly, if I want to tell you, that I am able to define also the reversible behavior, the effect of the hydromechanical coupled problem, and especially I can have it on the drying and on the wetting paths, and so I am able to almost explain all of the things that I have done for the permanent deformation. I am able to do it again for the reversible behavior. Some comparisons to just give more credits to what I have told you on the wetting, on the drying. One water content is going to be 11. You can see all of the calibrations that they are compared to the experimental results. So this slide, it can show the whole things that I have done on the wetting, on the drying. This was for the 11% and M4 material. I can show you the same also for another water content, 7%. This time again for M4, I think it's not M2, M4. There's a mistake here. M4 material, and so I have the same, let's say, results for material M4 at water contents of 7. And then I'm going to use to calibrate them with the Boyce model that I have shown you. And the next step is to inject my equation inside the code. This time I have used another structure, let's say UGM, the GNT material. I don't know whether you know it, the unbound granular material, that it was used for the granular layer, for the base layer, and then for the subgrade, it is the M4 material that we have used it for 2 types of pavement. We know all of the parameters for the reversible behavior of this material, that it is going to be modified by water content, the mesh, the geometry, the loading, and all of the things that you need to do for a numerical simulation. We have used the Cas3M software if you want for this simulation. And I finished my presentation as I promised. In this slide, you can see some numerical simulation that I can show you that there is a wetting and drying for both structure, because there are 2 structures that I have shown you. Let's say the hysteresis is more visible for structure 1, because the layer of subgrade is huger, and so we can have a huger hysteresis as well. And it is less evident for structure 2. So all of the things that I have told you, I finish with this conclusion that the soil is important, but don't forget that it's also the effect of the structure, the layers that you put, and how you combine these layers. And finally, there are some structures that they are more touched by the hysteresis, and there are the structures that they are less touched by hysteresis. And I will conclude the same, a linear approach that I proposed. It was defined first for the permanent deformation, and the reason was to present you a unique curve of SWRC that it is going to be used to express also the permanent deformation, and almost the same base was used also for the reversible behavior of the pavement of the granular material used in pavement structure. And another thing that I like also to do in all of my research work, that once you have a good analytical solution, once you know your material very well, don't hesitate to do some numerical simulations to express what you have found in the laboratory or analytically, to show it numerically also, and to bring some more information, because the numerical simulations, it's interesting. You can see several cases that they are generally hard to be studied experimentally, so you can express them with the numerical simulation. And there are the cases that maybe it is impossible to be done experimentally, that you can bring some answers numerically. And so this is the advantage, the power of the numerical simulations. And thanks again, Ellie, for your invitation. And I hope that you liked my presentation. It was useful. And so if there is any question, discussion, I am all available for the following part.
Thank you. Thank you so much, Hossein, for very informative and insightful presentation. I think it is it done a lot of work on that, and to really, it was very interesting that I see the approach that you developed, the linear approach. And so I want to know, before I also have one or two questions, but I want to know if among audience, is there anyone has any question? You might raise your hand directly and ask Hossein, or you can just type in the chat box. And yes, Haiba, please. Thank you.
Okay. Hello, Hossein.
Yeah.
Hello. Very nice to meet you, and very good presentation. I have one simple question. Yeah, because you did some research on the different water or different water content. Have you considered the free and soil behavior of the granular behavior on the deformation, or some cracking behavior of a pavement, free and soil behavior of this?
Actually, for the cracking, the cracking of the soil, the cracking of asphalt layer is somehow different from the soil. The granular material that it was studied in our work, they are supposed not to be really cracked, let's say. It's not in the family of the soil that it is considered to be the cracking soil, okay? So if I add, let's say, more fine content, if I'm going to change my soil to something like that, it is going toward the silty soil, or let's say the clay soil, yes, you're right, I may need also to take into account the cracking part. But for these materials, these granular materials that they were shown and they were studied in this work, let's say they are not in the category of the soil that they are going to show a very huge potential of cracking by time.
Okay. My question is the behavior of the free and soil behavior of
freeze and thaw, freezing and thawing cycle.
It's again the same, the freezing also, it is for some kind of silty soil that I'm going to have it, and these kinds of soil that we have studied, we don't have this potential of freezing. And even for cracking or freezing, it is not concerned. And especially the material that we use it in France, we don't have this problem. But you are right, if I'm going to change my material to something like silty material that with a very huge potential of freestyle capacity, yes, I need to do it. It is another project that I do it, but I didn't do it for the pavement, let's say. So maybe by time I'm going to combine it. But yes, you're right. If you when you do your pavement, generally you want to use the local soil. So for now, we use something like Misiac sand, or the soil that it is coming from this part of France. But if I change my material tomorrow and I'm going to use another sub-base layer that it is very silty, you are right, and don't forget that in Alsace region, the place that I'm living right now, the water level is very high. So if it's very high, it is going to come down and up and down very frequently. And so I'm going to have the problem. So all depends on my material. For the pavement, the the pavement that I have studied till now, I didn't have this problem because of the material. But for sure, why not? If I'm going to change my material, I need to take it into account. But I have done it in another project, let's say. Not
okay, thank you very much. Yeah.
Okay. Yeah. Thank you, Haibo, for the question. And I think that would be what Haibo is in fact suggested or proposed. I think it's a good topic, or maybe a good research for a joint maybe research collaboration with Hossein in the, because
I have the experience to work on freestyle materials, but as I told you, it was typically for another project that that for the tunneling, and it was really another topic that I have mentioned it. I can talk about it if you want. We can fix another appointment and we can talk about it.
Yes.
But for example, the water retention curve, because of the ice and because of the frozen soils, and you need to modify the things. I didn't bring it to the pavement, but I'm repeating. I know that I have the knowledge. If we need now to consider it for a pavement structure, why not? We need to do it also. It is possible to do it, let's say.
Yeah,
so
that's
if you are
great.
expert and if you are working on this field, I think that we have the possibility to work together very soon. Yes.
Sure, of course, because as Haibo mentioned, freezing thaw cycling are very important in pavement structures because it will be the initial reason or the starting of the pavement structure failure, or which this kind of as we said, the freeze thaw cycle will be at the end will be extend to the pavement surface at the end, and so many cracks that we see, especially in cold regions, is one of the issue is because of the freeze thaw cycles during the spring or winter. And also another issue, as you mentioned, about the wet drying cycle and the rotting or permanent the deformation that we also see in pavement, which is one of the first reason or the initial reason will the soil weather problem issue regarding to the compaction, or the again wet drying cycle that may cause permanent deformation in the pavement structure. So these are very a matter of concern for us as a pavement engineer and who are working in pavement and should be deal with it.
Right. Actually, I'm very interested on the topic. So if I'm going to say very shortly and briefly, you're right, because I didn't consider the frozen soils in this work. And you're right that another issue, challenging point that it can be added, that for the, because of the weather condition, because of all of the things we have didn't consider it. But you are right, there are the seasons that the winter, you should consider the frozen soils, you should go through the negative temperatures, and you should consider all of these things. You are right, there are the issues. And today you give me a new title, let's say. Because
yes,
because of all of the things done, and with pleasure, if we can do something together, it's going to be
I hope so. Yes.
Yeah,
sure.
It's a very good challenge, let's say.
Yeah, I hope so. Yes, hopefully we will talk more on that, hopefully for our future collaboration. So I think we are running out of time, and so already 10
Sorry,
minutes
I was a little bit long, I think.
No, it was, I think from the beginning we have some issue, but it was okay. Really, it was informative, and it worth it, I can say, because really, I myself, when I listen and saw your presentation, it was really informative, and so many ideas, as I mentioned, just it's come out from my mind. Okay, what we can do in our pavements and relating to subgrade, and which is very important thing in the pavement, subgrade foundation of the pavement.
If you have any problem related to soil, it's going to be a pleasure. We can work together.
So sure. Of course, I'm looking forward to that.
I am in, let's say.
Sure. Thank you. I appreciate really for your approach. Okay. So any other question? Although we have no time among audience, no question. Okay, so I think it's already
there is
finished.
One hand raised. So
yes,
maybe
Rabi.
You have a
yes, Rabi, please.
Yeah, thank you, Doctor, for your presentation. Actually, I want to ask about the effect of another type of soil, or also the level of stresses. Also, I mean, in determine the value of the permanent deformation. Did you consider that in this study, or?
Actually, you know, in this work that I have shown you, we have our soil. We know this soil from several years, and this is, you know, the material that it is generally used in the pavement structure in France. If your question is about another material, there are some other tests done almost in the on the different material done on the same, let's say, experimental condition that they're existing in the literature. If I try to combine all of these results and to provide in something that it is going to be more general, no, I didn't do it because I had already enough experimental results to construct my theoretical approach. But maybe another issue is going to see who has done what, and so to combine, and so something like it's very, let's say, we do it very often right now. So the artificial intelligence, you know, the machine learning, and so to try, you know, to bring to find a common theoretical approach and to apply to the different materials that they are expressed in the same, almost the same experimental condition, and so to provide something more general. Why not? Why not?
Okay, thank you, Doctor. Thank you.
You're welcome.
Thank you, Ravi, for your question. Okay, other questions? Okay, so I think no more question. Okay, thank you so much, really, Hossein.
So again, for your invitation, and so happy to be with you. And I hope that the presentation, because even with the problem of slides, that it was not full. I don't know why it didn't work, but finally.
Yeah, I think maybe I have. Are you using on web version of the Teams?
I am using on the web version of the Teams, yes.
Okay, so I think that is the reason, because when you
use I should have been connected, but you know, I have just do the link that you have sent to me, and so I was connected. But I may change it next time, because you know, I have two computers. There is one that I have my Teams, and the other that I use the connection. So I think that I should have used the other one, but finally it was done. So you have seen the
It was on, that's it.
Just tell me that you have seen the slide. So good.
Yes, that's right. Yeah,
but next time I will pay attention to this. Okay.
Okay, great. Thank you. Anyway, so really thank you, Hossein, for your time. I know it was early morning back in France, and
but thanks to you, because but I wake up every day by 6-7, so it was not very early for me. But but anyway. But I was just a little bit afraid that my sound will be somehow sleepy, and so it's. I hope that it was not the case, and so you.
Very energetic. Your voice, your sound was very energetic, full of enthusiasm.
So I'm happy that even at 8 o'clock in the morning, so I was able
you are
to
a very good instructor, and so this is something shows also your capabilities as a.
But thanks again. Thanks again for your invitation, and so hope that it was something like useful for your side.
Yeah, sure. Thank you. And by the way, some audience ask if we can have a copy of your presentation.
I will send it to you, the link, and so if you want to share it with the others, with pleasure, no problem.
Okay. Thank you.
So,
thank you.
Just if you see that it is becoming late, ask me. I will send you as soon as
possible. Sure. Thank you so much.
I will try to do it in the day. You are welcome. Have a nice.
Thank you, Hossein.
We say have a nice weekend. I don't know, but I know in China you work even Saturday and Sunday, so I don't know. I should ask. I should tell that happy weekend. But anyway, hope to see you very soon. And again, thanks for the chance that you gave me.
It's our pleasure. Thank you everyone for attending this webinar. Hope to see you in the upcoming webinars, and thanks to Hossein for his presentation and his very nice speech. Everyone, have a good day, and
bye. Thanks again.
Bye. See you next time.
Soon.
Thank you.
Thanks again.
Thank you,
bye.
Bye.